Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending our special presentation featuring technology demonstrations of plasma and flame surface treating for improved adhesion. We're very excited to share our insights today. You'll be seeing 4 new videos of surface treating technologies in action and receive expert tips on implementing these technologies. Please note this webinar is being recorded, and you'll be able to access both the recording and presentation slides once they are available online, usually within 24 hours. If you have any questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the webinar. We'll reserve time at the end of the presentation to answer as many questions as we can. All attendees to today's webinar will also receive a personalized certificate recognizing their participation in today's event. Enercon is pleased to provide this informative presentation to you today. Our family-owned company was established in 1974, and our corporate headquarters is located in Menomonee Falls, Wisconsin. Today, Enercon serves the global marketplace with innovative technology solutions with operations in North America, Europe, and Asia. Today's presentation will cover plasma basics, such as what is plasma and what does it do to a surface to improve adhesion. We'll look at 3 distinct forms of plasma treatment: blown arc, blown ion, and flame. You'll see these technologies in action and discover how manufacturers integrate these systems into their production lines. We'll also look at methods used to measure the changes in surface energy imparted by plasma and flame surface treatment. And we'll wrap up with an opportunity for you to post questions to our expert presenter. Who is our presenter? I'm glad you asked. Wilson Lee will be our guide for today's journey into the world of surface treating. Wilson is Enercon's Business Development Director and one of the industry's foremost experts on implementing surface treating solutions to improve adhesion. He works with clients around the world to solve application challenges and improve their productivity. Wilson earned an electrical engineering degree and an MBA from Clemson University. With that, I'll turn it over to Wilson.
All right, well, thank you, Mark. Hopefully I can live up to that introduction. That was very nice. I appreciate that. As he mentioned, we're going to do things a little different today. We are going to go, as we usually do, and talk a little bit about plasma right here at the beginning so that we'll all be on the same page about what plasma is and does. But then we are going to go to some videos that we've taken in our lab. Obviously, in today's world, it's hard to get out and demonstrate the technologies that we have, the blown arc, the blown ion, and flame. So we decided to put this together so that you could go into our lab, have someone walk you through what the needs are for each of the units and how they operate, and so see a video of those things instead of just listening to me talk the whole time. So let's get started. Who's using plasma? Well, pretty much everyone. It's hard to imagine an industry right now that's not printing on something, painting something, coating something, or bonding something. So again, automotive is certainly a big one. There's a lot of electrical potting application, window and door, wire and cable, but just about anybody that's printing or bonding or coating is possibly using plasma, or it's at least an option. May not always be the best option, depending on volumes and things like that, but we see a lot of people changing from other forms of wet chemistries, solvents and primers, or ablation or sanding, and moving towards plasma because the advantage that plasma has is what we're going to discuss in the next slide, is repeatability. So why are they using plasma? We can create stronger bonds. We can reduce the material cost. Sometimes that might be in reduction of waste. It might also be in reduction of inks and adhesives, because it usually takes less once you've got a good surface in order to get that good bond that we're looking for. These things increase throughput. Our process compared to others that we've mentioned, like hand prep, is generally faster. So we can increase your productivity. And also, it's a very repeatable process. If the material's coming in and it's consistently coming in, it's going to leave our system very consistent as well. And this improves overall product quality. So those are the things that, the reasons I should say that people are switching away from older methods to more modern plasma flame type treating methods. A little bit about adhesion. There's 2 forces at play here. You look at the liquid drop on the left, you've got the cohesive forces. Those are the forces holding the liquid together, whether that liquid is your paint or your coating or your adhesive or maybe just water in this case. That holds that together. Then you have the adhesive forces. That is the force between the liquid, the ink, the paint, the coating, and the surface of the material. So what we're trying to do is when we increase the surface energy, you want to see what you see on the right there, the treated side, you want it to be fully wet. That means that you have increased the adhesive forces in this equation to be greater than that of the cohesive forces of the liquid. So that gives you better wetting. The example we always use is Rain-X in your windshield or washing your car. You're actually just putting a barrier on there that has a very low surface energy. So you get the untreated version over on the right where the surface beads up and simply just rolls off your car. But as it gets dirty and as that coating starts to wear off over time, the surface energy will go back to its normal state, which is a little bit higher, and it will be a little bit more wettable. So that's the two forces that are in play, and we have to deal with these and measure these in certain ways to figure out what kind of surface we're going to have and how we're going to bond your surface as we move forward. How do we measure these? Well, we have dyne and contact angle are the two main tools that we use. Up top, you see the dyne ink pens that we provide on our website. So let's say you've got, you want to test your surface. You take the 44 pen, which is right there in the middle, and I draw a line. I draw the bottom one, and it has correct dyne level. If I draw that line with that pen and it stays solid like that for 2 seconds, that is, you have said to be passing 44 dyne. So that means your surface energy is at least greater than 44 dyne. So let's test another one. The one below the 44 pen is a 60, that's a higher dyne. So let's say you use the same test, you take the 60 and you drew the line, and now you get the one on top. That means you have failed. So that means now you know your surface is at least 44 dyne, but it's not 60 dyne. So what a manufacturer might do, they may have already predetermined that they need to be, say, above 50 dyne to get a good contact angle, and they want to do some spot checking. So they'll just have some 50 dyne ink or a 50 dyne pen, and every now and then they'll go check their surface. And as long as you get the bottom line there for 2 seconds, you know that you are at least above 50 dyne. And that's something we can help you do as well. All of our processes are 2 steps. One, we prove that plasma or flame works in your application. And then second, we work with you to try to make sure that it's repeatable. And that's by making sure that we're getting you up to a surface energy that will give you the best possible results. Also in our lab, we use both the BTG Surface Analyst on the left and the Cruise Mobile Surface Analyzer on the right. These are both excellent tools. They go out a little bit differently, and so they have different, we use them in different applications. The Cruise is a ballistic drop angle, contact angle measurement tool. You'll see from the picture you're looking at the top, it knows precisely how much water it's putting on the surface. Then it measures the diameter of that, and it can calculate what the contact angle is. The Cruise is a more traditional method from a goniometer point of view. You drop the liquid on the surface, and then you take a picture of it from the side, and you measure the contact angle. So the top picture on the right there is about 90-degree contact angle. That would be prior to treatment in most cases, and then after you've treated the surface, you can see that it is about 40, 41 degrees on the bottom. That means you're getting better wettability. So those are the ways that we measure surface energy, and using contact angle and dyne are both acceptable ways to do that. So let's talk about the different types of plasma. Excuse me. The blown arc air plasma. This is, you can see it down there on the right. All of our systems, even if it's a single or a dual head, it's going to come in that cabinet. That is the Pro Series. You can tell by the touchscreen. And this is the dual head version. So we can treat out to 7 inches wide on this. Non-conductive materials. We can treat a lot of different materials for printing applications or labeling applications. But let's go to the lab and look at the video real quick, and let's talk a little bit about the blown arc.
Today we are introducing you to Enercon's blown arc plasma surface treater. The primary components are the power supply, integrated HMI, and discharge head. Each power supply is available with 1 or 2 discharge heads that can come in 6 or 12-foot lengths. These systems are designed to run on a wide range of voltages to meet your needs and also require 70 to 90 psi of clean, dry, oil-free air. When setting up your blown arc system, you will want to adjust the head to be approximately 3/4 of an inch above the surface to be treated. How blown arc air plasma works. Blown arc air plasma is formed by blowing atmospheric air past 2 high voltage electrodes and is sometimes referred to as corona treatment. The electrical discharge positively charges the ion particles surrounding it. Through direct contact, these particles positively charge the treated area of the object's surface. This makes the surface more receptive to any applied substance, such as inks and coatings. The discharge created treats up to 3.5 inches wide and is suitable for treating non-metallized surfaces. Typical application speeds are between 5 and 15 feet per minute.
Enercon uses a variety of methods to determine the effectiveness of surface treatment in our labs, including measurements for dye level, contact angle, and surface polarity.
Okay, so to summarize what you saw there, again, the blown ion treats out to about 3.5 inches, 7 inches if you use a dual head, non-conductive surfaces, and it's relatively slow process speed, 5 to 15 feet per minute, although there are things that we can do. You can use banks of these to go faster. You can rotate the head a different way in certain applications and go a little faster. So there's a lot of ways that we can use this. Let's show an application real quick. This is one that is very common. This is just a pad printing on a toothbrush. So you see down here, we're treating it with the blown arc as it goes around, and this rotary table spins and does the different things to the toothbrush that it needs to do to manufacture it. And one of those steps is to print the label onto the toothbrush itself. So it's pre-treated with plasma, and then it goes under the pad printing and gets its logo. So now let's go to the blown ion air plasma. This is what most people think of when they think of plasma. It treats about 1/2 inch, give or take. You can pretty much treat any material that can handle the temperature. The temperature is about 120 degrees, but you're usually going very fast. So it's for precise patterns in small spot areas inside crevices. The minimum dwell time is the reason we can use very high speed. So we're usually talking 50 to maybe even as much as 150 feet per minute with the blown ion air plasma. And that's what we mean by very high speed. So generally, we're not imparting that much of a delta T or increased temperature onto the surface as it's going by at say 100 feet per minute. So let's go ahead and watch the blown ion video.
Today we are introducing you to Enercon's blown ion plasma surface treater mounted on optional cart. The primary components of this unit is the power supply, integrated HMI, and discharge heads. 1 or 2 are available. Discharge heads are available in 6, 12, or 18-foot lengths. The system requires input power, but we have designed the system to work on a wide range for your needs, and it also requires 70 to 90 psi of clean, dry, oil-free air. For optimal treating results, when setting up your blown ion discharge head, set it 3/8 to 5/8 of an inch from the surface to be treated. How blown ion air plasma works. Blown ion air plasma systems push pressurized air past a single electrode, which discharges inside the treater head. The electrode creates positively charged ions in the surrounding air particles. The air pressure forces the air particles to accelerate out the tip of the head as a high velocity stream of charged ions directed towards the substrate surface. Through direct contact, these particles positively charge the object's surface, increasing its surface energy and making it more receptive to inks and coatings. The blown ion 125 treats up to 1/2 inch and is effective on most conductive and non-conductive materials. Typical speed ranges from 50 to 150 feet per minute.
Enercon uses a variety of methods to determine the effectiveness of surface treatment in our labs, including measurements for dye level, contact angle, and surface polarity.
Okay, so to summarize that, again, you can use this on almost any material as long as it's not a very thin film going at a slow speed. You saw there on the last two videos, I failed to mention in that first video, you saw the demonstration of how the BTG device works. That was a video on using the cruise to measure surface energy. But again, precise spots, very high speed. The dual head system over there on the right, you can see can treat about 1 inch wide, or you can put them in parallel and go up to say 200 to 300 feet a minute for faster processing speeds. So again, the blown ions, what most people think of when they think of plasma. Let's look at a couple of applications. This is what I usually say is one of the original automotive applications. Older headlamps would tend to leak because the seal with the housing that it had was not very good until they started treating the housing with plasma. So what we do is we use a blown ion to treat not this portion of it, but the portion that this headlamp is going to go into, which is just a plastic housing. We treat that and go around that, and now we have a much better bond. And so the old problem of the headlamps filling up with water is generally not a problem anymore. So again, this is a perfect application for a blown ion. The adhesive line that you use is about the same width as what we're treating with the blown ion. So it makes for a very, very good fit as far as the application is concerned. The other one is this again is a glue line application. This is for a spoiler assembly. And again, this is a very common setup when you're dealing with plasma and you're trying to bond something. So you have the adhesive dispenser over here, and it's immediately preceded, I should say, by the blown ion in this case, and it's going to treat about a ½ inch. We're going to lay the glue line, which is going to be a little bit less than that. And now you've got a very good surface for which that glue line is going on to, and you're going to have a much higher bond strength as a result. Just this is a relatively new slide for us. This is something that we've been working on recently with some window and door manufacturers and some other manufacturers that have multiple areas that they need to treat, but they have a small window to get in there. Window and door is a perfect example. So we have these custom nozzles, and this is not all of them. This is just some of them we have. If you have a need where you're looking to treat 2 areas at one time, but you can't fit 2 nozzles down in there, or maybe 4 areas, this might be an option for you. So just reach out for me, we'll get in touch, or reach out for your regional manager or your rep, and we can get in touch with the product manager, and we can design anything that you would like. But this is something relatively new for us. We're having some very good success, especially in certain markets where you have very tight areas and you need to treat multiple sides of a part. Lastly, while we're still talking about the blown ion, we should mention the blown ion 500. This is also the very same. It's kind of like the grown-up version of the blown ion 125. It treats 2 inches wide. It is a 6-port, or we call multi-port unit. These are offset ports, but each one of these discharges is the same power as the blown ion 125, which is a 500-watt system. So this is a 3 kilowatt system. This is very good for treating wide areas at very high speeds. You can put a linear nozzle on there if you wanted to and run it parallel to, say, a very, very fast wire and cable line that might be going 1,000 feet per minute or more. So there's a lot of opportunities with this unit. Our competition generally goes wider with plasma by spinning a single head around some sort of axis or 2 heads that they might put on there. So the difference there is treatment speeds. Those might work really well on a very thin film because the temperature difference is a little bit less than what we're putting on the surface, but they're not getting anywhere near the ion density. So if you're treating metals or plastics or solid pieces and you need to go very fast, this is definitely a good way to go. And you're getting significantly higher ion density on that surface. Finally, we're going to go to the flame plasma. So again, we usually use a mixture of air and natural gas or propane. It's also a very high speed unit. We have them on the right there. You see the cart with the hood. These are things that we can do as well that you can move around. That last video I should have mentioned with the blown ion, it was on the cart. He mentioned the optional cart there as well. So we have customers who are using that and moving it around when they need to treat different lines. And the flame system here can be done the same way. You can raise and lower that depending on the conveyor height, or you can move it around to different lines as needed. Flame is great for multi-dimensional surfaces, whereas with the blown arc and the blown ion, we have to be very conscious of the distance from the surface. Flame, especially with some of our more powerful burners, can allow you to treat, and you might have a 2, 3, 4, 5, 6-inch window there where you're getting a very consistent treatment on that surface. So let's go to the video, and let me pull that up real quick.
Today we are introducing you to the Enercon Flame Series Pro Surface Treater. The primary components are the power supply, integrated HMI, and burner heads. These systems require either 108 to 132 volts or 216 to 264 volts for input power, 75 to 115 psi of clean, dry, oil-free air, and 0.75 to 1.5 psi of natural or propane gas. These units come in 3 sizes: DF100, DF200, and DF400. Can offer either 1 or 2 burner heads per power supply, and burner heads come in standard hose lengths of 6, 12, or 15 feet. Burners come in 2 styles, the 24 series and the 226 series. 24 series burners are used in applications where the burner will be stationary, and the 226 series is for use in setups that require the burner to be moved, such as being mounted on a robotic arm. For optimal treating results, the burner should be positioned 1 to 4 inches above the surface of the material to be treated. This will depend on the material being treated and the burner style being used. Typical line speeds are 50 plus feet per minute.
Enercon uses a variety of methods to determine the effectiveness of surface treatment in our labs, including measurements for dye level, contact angle, and surface polarity.
Okay, so one more video there about how to operate the flame systems. We'll summarize again. Again, it's very high-speed applications. We can treat as wide as you really want to treat. Above 16 inches, we need to go to either a dual head system or a water-cooled system, but we have both. Generally, when somebody wants to treat maybe 20, 22 inches, we just go with a dual head system that has maybe 2 11 or 12-inch burners, and that's just an easier application than going with the water-cooled head. But we do have situations where the water-cooled head is necessary, and in that case, we can go out as wide as you like. Again, you do have a nice wide area there that you can treat. So when you're treating a multi-dimensional surface, like we'll see in a couple of our applications in a second, it is very easy to treat those and not have to be concerned about your distance from that surface. So let's look at a couple applications. This is an interior door panel and dashboard. Again, you see the dashboard over here with the robotic arm. Obviously, there's a lot of different dimensions on this that have to be treated before you put the decorative coating on that. We generally have a cycle time here of roughly 45 seconds or so. So we need to use a flame in this application. This is usually made of a fiberglass or polypropylene, and then it's treated and then again decorated. And then these are the door panels over here. So you'll have a cell. A worker will come in and put these on the mounting sections, like here or here, and then close the cell. The robot will start up and go and treat those, and then they'll pull them out. So usually we're treating these in much less than 45 seconds, but the cycle time to get them in and out is usually about a 45-second time frame. Again, then the adhesive coating is applied, and then the decorative coating goes on top of that. Another one is door skins. Again, you can see over here we have multiple dimensions, and we could do this with plasma. With plasma, but it would be more challenging. It would take longer. It would be larger heads. It would take us much longer to treat this door with even the blown ion 500. We probably would take 2 or 3 minutes to treat this door, whereas with a flame system we can treat it in 15 or 20 seconds. We measured this one. The initial contact angle on this skin was at 22 and 85, and then the final contact angle after treatment was down to 22. So you got much better wettability, much higher surface energy, and so that coating is going to stay on that door much longer. Another application that can be used with both flame and plasma is electrical circuits, electrical coatings. Many circuit boards are either coated after they are manufactured, or if they're going in an outdoor assembly, they may be potted. And so you will see them in some sort of plastic container or metal container, and then they'll fill that with an epoxy that will harden and protect that circuit from the weather, from rain or exposure. So this is also an excellent application. One thing we have to keep in mind is generally it's very easy to treat the circuit board itself. It's the vertical walls that sometimes can be a challenge. So there are things that we can do with dual head systems that are angled slightly so that you're hitting those leading and trailing walls as they go by. Changing the direction or the angle that the part goes into the flame also will help. So there's some games that we can play to help get a better bond inside that vertical wall. The one thing about flame and plasma is we call them line of sight type treatments, which means if you're not looking at it, you're not treating it. So again, a vertical wall is a little bit more of a challenge, but there are ways around that. So just keep that in mind. And if you have any questions about that, please feel free to let me know. Now we're going to show one final video. It's a show video that we typically use that's got a bunch of applications in there. And you'll hear me talking over that video and talking about what each of those applications are.
This is a group of short videos to show the different technologies that we have and some different applications. This might be running on a trade show video monitor that we use. You can see the blown arc and the blown ion, and now the flame systems operating. This is a dyne test on what it looks like if passed on the treated side and what it looks like on the untreated. We're printing on the bottom of these bottles, pre-treating it with a blown ion so that it has good surface energy. This is a terminal block application where we're printing on these terminal blocks. This particular block does not have any pre-treatment with plasma, so the ink is easily removed. This terminal block has been treated with plasma, so with the tape test, you'll see that we have much better print adhesion. This is an automotive application using a flame treater with a robot. Cycle times are generally very short, and we have a lot of multi-dimensional surfaces here, so flame is perfect for this application. You can do this in roughly 45 seconds. This is a high-speed box application. For wider applications, we use the blown ion 500 to treat out to 2 inches wide. Here we're using the BTG surface analyst to measure the surface energy, in this case using contact angle. And finally, an animation showing the plasma stream and the surface down below when, as we're treating it, we're cleaning, etching, and functionalizing the surface.
All right, that was our final video. Some key topic review real quick. We provide many technologies to increase the surface energy for better bonding, coating, painting, printing, cleaning, just about anything that we need to do to the surface. Plasma and flame are generally good options to make that surface as repeatable as possible, and better that surface, the better your product's going to be. The individual application generally determines on its own what type of system we're going to use. I generally say I have to ask a lot of questions when people call about what they're trying to do, how much area they're trying to cover. If you're only trying to cover a few square centimeters and you've got a couple of minutes to do it, well, we've got lots of options that'll do that. It just depends on how you want to integrate that into your system. However, with say a dashboard like you saw in that last video, if you need to treat a few square feet and you've only got a few seconds to do that, then you're going to have fewer options, but we still have solutions for you. So generally, after asking a couple of questions about your application, I can tell you whether the blown arc or the blown ion or the flame is going to be the better choice there. We also have a lab in Menominee Falls, and we also have reps around North America and Europe and India that have units that can be brought to your facility for testing. So if it's not, obviously with the world today, it might not be possible to come into your facility and run the trial, but most of the time we can run that for you in our lab. So reach out for me. We'll get you an RMA, bring your parts in. We can determine which is the best way if we don't know prior to treating, and we can, again, give you the lab results, give you all the data that you need using the devices that we talked about to measure surface energy, and make suggestions and try to help you with the integration. With that, Mark's going to come back on and see what kind of questions you have.
All right, thanks, Wilson. Yeah, we've got quite a few questions here. The first one is, can you talk a little bit about the lasting of the surface treatment energy over time? How long do you generally have between treating and adhesive application to maintain effective bonding?
Well, that's two questions. So let's talk about the effective bonding first. To get your effective bond, we would always recommend that you surface treat immediately before bonding. That's going to be your best method. That is going to get you at your highest surface energy level, and it reduces variability in your process, because there are, obviously, the more you handle something, the longer, if it's batched, those things are introducing things that you can't control. So we would like you to bond immediately, or paint or coat or print immediately after treatment. Now, sometimes obviously that's not possible. Most materials are stable in the range of hours to days. If you're treating fluoropolymers, they're only stable for a few seconds. So PTFE does not treat very well. But if you're treating polypropylene or aluminum or something like that, generally you have 24, 36, 72 hours before it really starts to fall off. And so let's just use dyne for an example. Let's say you start at 30 dyne, you treat it, it goes up to 60 dyne. It'll steady state at 60 dyne for, again, maybe 24 to 48 hours. And then it'll start to fall, and it'll steady state again somewhere above where you started generally. So again, if you started at 30, it goes up to 60, it may steady at about 40. So occasionally 40 is enough dyne, enough surface energy measured in dyne that you can print on it. In that case, you have a batch application where you can treat them all at once and then print on them as needed. This doesn't happen very often, but it does happen occasionally. So again, you probably have hours to days, but you would probably rather bond immediately after or as soon as possible after treatment.
All right, Wilson, we have a couple questions related to metals. Can you improve the bond between metals to plastic by plasma treating the metals? This would be for an insert molding metal in plastic. And then another related question to metals, is treatment effective on metals like zinc and chromium?
I have not tried zinc and chromium. So we have a lab, so we can definitely try that. Some minerals like that do not treat particularly well. And so we would just have to get in the lab and see. But again, we have all the tools there, or if we want to bring it out to your facility, we can do that. So just let me know if you want to test that. Going back to the metals and the plastics, metals generally have a higher surface energy than plastics. It's just in the way the bonding of the molecules work between the different substances. So again, if I'm having a block of titanium and a block of polypropylene, the titanium is going to have a higher surface energy. So you could probably, there's applications where you're just treating one, and if you're just going to treat one, you would probably end up treating the plastic in this case, because that's the greater chance of having lower surface energy. But you would probably want to bond those two together and then do a pull test of some sort and see what kind of failure you get. If you think back to the slide where I showed the cohesive and adhesive forces, you see assume that for a second that is an adhesive. If you break the two parts and you see adhesive on both sides of the part, that means you've got cohesive failure, and that's what you're looking for in most cases. That means that you are breaking it at the maximum strength of the adhesive. If you break it and you pull all the adhesive off of one side, and if you didn't treat this, I'm almost positive if you broke that, you would pull all of the adhesive off the plastic side. That is an adhesive failure, or an adhesive failure, and that means that you're probably going to need to treat the side that it's pulling off on. But in that case, we have people that treat just one side or treat both sides. Just kind of depends on how your system works. But again, treating the lower surface energy material is probably the one that I would treat if I only could treat one.
Thanks, Wilson. Are there any concerns with electrical damage when treating PCB assemblies?
No. There is a small voltage associated with the electrons that are going through the plasma, but no, we have not had any issues damaging PCBs in our with either flame or with plasma.
Does plasma treatment work on glass fibers?
Yes, plasma works very well on glass, and if you start to introduce glass, like in a glass-filled nylon or something like that, the higher the percentage of glass, generally the better the treatment. So glass treats extremely well. In automotive applications and windshields, you're generally starting with a contact angle in the 50, 60, 70 range, and after treatment, it's almost completely water wet. It goes down to below 10 on contact angle. So glass treats extremely well.
Have you seen any of these treatment methods used to achieve irreversible bonding of silicone to plastic?
I'm not sure I understand the question necessarily. Irreversible, you can always break something, but it should be, once you've treated something and bonded something, your surface energy in between those bonds doesn't degrade over time unless there's an additive that's going to eat away at the adhesive, and that does happen occasionally. So I mean, you put additives in plastics all the time, whether it's a flame retardant or some temperature concern that you might have, so that you want the plastic to perform better at very high temperatures or very low temperatures. Some of those things can start to attack the adhesive after the fact, but most of the time, after you have bonded it, you don't have to worry about the degradation in surface energy of that surface anymore. And I hope that answered that question. And if it does not, feel free to send me an email after this and we can discuss more specifically.
Have you run into applications where cleaning or pre-treatment is needed before treating with plasma?
Absolutely, especially with mold releases and things like that. Plasma does a good job cleaning, and so does flame, I should say. They both clean organics very well, like fingerprints and things like that. They don't do as well with inorganic materials, but it has to do mostly with how much inorganic material is on there and how long I had to clean it. If it's a very slow application, for instance, I had an application once where we were cleaning wire, but it was actually moving relatively slowly. So we were able to put a couple of plasma heads on that and clean off that wire before the jacket was put on it. But because the amount of oil that was on that as they drew down the wire was not very much. So in that case, at that speed, we were able to do it. So when you're talking about inorganic materials, if I've got some time, I can clean off a lot of things with plasma. But generally speaking, if it's going pretty fast, then you might have to add a step, a cleaning step, whether that's some sort of bath or a CO2 cleaning or something like that.
All right. It's interesting, Wilson, as we get deeper into the questions, we actually have more questions now than when we started. This question is about, could you give some more info on the technical differences between the first two systems? Maybe specific examples to understand the different applications for each. I'm pretty sure that was the blown arc versus blown ion plasma.
Yeah, first off, the blown arc, just from the way that the electrodes are positioned and the way we blow the air through that, it is very easy for that to arc to an electrical circuit, or to anything conductive. So we avoid anything conductive. One of the first questions we always ask is, what's the material? And if it's conductive, we just do not use the blown arc. It can cause damage sometimes to the blown arc itself, depending on how long it arcs to the surface. And so we just try to avoid that. It's also a much slower application. So again, 5 to 15 feet a minute just doesn't work on a high-speed wire line. So even if I turn it 90 degrees, sometimes that works for a printing application, but generally if we're talking about something something fast, then we're going to have to go with the blown ion because it's just a much more intense. The ion density is much higher. It's more concentrated in a much smaller area of about a circle about a half an inch wide versus a line that's 3.5 inches long by a half inch wide. So you can just, the density of ions on the surface is much greater with the blown ion. So again, they will both work in a lot of cases if it's a plastic. So we're generally looking at what makes the most sense. Again, I asked the question, how big of an area do I need to treat and how fast do I need to treat it? Also, the blown arc is a less expensive technology than the blown ion. So if I'm treating a large area and I have time to do it, it just is more economical to use the blown arc in that situation. So there's a lot of moving parts there that will take us to the right technology. It's just, let me know what you're trying to do, and I can recommend a system.
All right, here's a person looking for a recommendation. Would the plasma arc be better than just flame treatment for treating HDPE bottles for enabling label adhesion, and would it be a cost-effective change?
Generally, when you're labeling bottles, flame is the best way to go because generally the speed is the limiting factor. You could possibly do it with the blown arc, but you have to be too close to the bottle. So again, especially if you're printing 360 degrees around the bottle, you either need to be spinning that bottle or you're going to have to go into a bank of possibly 4 flame heads in order to make sure that you're getting all 360 degrees around the outside of that bottle. So I would generally think that since you would need multiple multiple blown ion heads to do that, and you would probably have to have multiple stations, I don't think it's more economical to go from flame to the blown ion, or the blown arc, I should say, in that situation. So certainly something to try. It depends on how fast your line's moving and whether or not your bottle's spinning. It looks like that we had a phone line go down and on Mark. So I'm going to see if I can find the questions on my screen until he pops back on. Unfortunately, the questions are not on my screen. So we'll go back to that last question about bottles. We do a lot of printing on bottles. And so again, a lot of them are very high speed applications. The one we were working on in the lab about 2 weeks ago, you only had about 1/5 of a second to actually treat that bottle, and it was spinning. So in that case, we went much faster, and we were able to use flame treatment to do that. But in that case, you would never be able to use a blown arc. Mark, it sounds like you're back.
I am back. Next question: do the discharge heads ever wear out or become less effective?
There are occasions when the blown arc head needs to be replaced. If things are being blown up onto the surface, it eventually can be damaged. Most of the time, the nozzle that we use on our blown ion does not need to be replaced. It is a part that we can replace, but generally the electrode is what you're having to replace in the blown ion. And that's about a 2,000 hour replacement.
What temperatures do plasma-treated surfaces reach?
Depends on the speed. With flame, the flame itself is about 1900 degrees C, but again, you're running by something, you're usually going around 50 to 150 feet a minute going by. So you may increase the surface there by 10 to 20 degrees C as it's going by. Plasma is not nearly as hot. Inside the chamber, plasma is 450, 500 degrees C. At the normal treat distance, which is 1/2 inch on the blown ion and 3/4 inch on the blown arc, you're only at about 120 C. So the delta T onto the surface is less. But again, it all depends on how fast you're moving. If I'm going 200 feet a minute, then I'm only raising it a couple of degrees. If I'm going 25 feet a minute, then I might actually increase this 10 or 15 degrees. So we just have to keep that in mind when we're treating. The only time that really comes into play very much is on a thin film, a 1 or 2 or 3 mil film. like a PET or something like that that has a very low melting point.
Can you apply these technologies on surfaces of cellulose, such as paper and cotton cloth?
Yes, on both. The box application, a lot of boulder gluers, as they're called in the boxing world, they're made out of cardboard. And so those are treated before the glue line goes on, gives you a better bond. And what was the second one? It was a tissue?
Cloth.
Cloth. Textiles, not as much. You can do it, but generally when somebody's calling me about textiles, they're wanting to add a coating to the textile. They either make it waterproof or something like that, or they're wanting to do other things. So textiles are a little more challenging. Usually they're wide. They're wanting to treat them at the full width, and that's a challenge because it's just more expensive to treat 3 or 4 or 5 feet wide. If you're only treating a certain area, then that's certainly possible. It does take the plasma. It does increase the surface energy. It is not permanent, so it is more challenging. The other problem with something like that with a textile is obviously, again, line of sight. So I'm only treating a portion, a very top portion of that, and I'm not doing a very good job getting down into the fibers. To do that, you would need to go with some sort of roll-to-roll low pressure unit.
We have someone that is trying to bond a UV adhesive to a urethane tube. They've used blown arc style plasma, and they do achieve a 56 dyne level, but they have delamination under pressure. Would additional plasma passes help with eliminating the delamination?
It's possible. It depends on how close we're getting to your maximum treatable number on that surface. I think you said 56 dyne. It's possible using a different technology, we might could get that up into the 60s, and that might help. You can also, if you have the ability to control the speed, you could slow down, and that would increase the overall treatment of the surface, and then maybe do some tests that way. Other than that, then I think we'd probably need to get a blown ion type system into your facility and run it that way and see if we can achieve a little higher dyne levels. But yeah, the longer the exposure, the greater the dyne is going to be. But you're only going to go so far. You can only there's definitely diminishing returns the second time you treat it and the third time you treat it. You're going to finally get to a point where you've overtreated the surface.
Is it possible to activate surfaces enough to enable bonding without additional adhesives?
We do have a couple of applications. Filters come to mind where we are using flame or plasma and we're just heating up the surface to where it flows, and then they're not using adhesives. But no, generally, what we're doing to the surface is not making two things bond together. So there's generally, unless you're, again, melting something and intentionally doing that to make the filter, you're going to have to use an adhesive. Now, you may be able to use less. That happens all the time. I've had applications where customers have come back and said we can use 40% less adhesive than we were before, and that's due to the wetting. Again, if you can imagine, and that, again, going back to that picture where the cohesive forces, in the one picture that you see the little slide that's got the treated side and the untreated side, and you've got good wetting. One thing you notice in that is that the thickness of the wetted surface is much, much thinner than that of the untreated surface. So it's going to take more adhesive in that untreated surface to achieve any sort of bond. And that is a thicker layer of adhesive, and the thicker that layer of adhesive, the easier it can break in different axes. So you can use less adhesive in certain cases, on certain occasions, and that can be beneficial to your bond strength.
Next question is, can different gases such as forming gas or argon be used with your equipment?
Yes, forming gas, there is a change that has to be made with the electrode assembly on our plasma system, just because of the distance it needs to be from the arc to create that with forming gas. Argon is a little bit different. Noble gases ignite or change to an ion at a much lower voltage than our other systems. So we use what we call a VCP, variable chemistry plasma system. And that is basically just an adjustment that we've made to the system, and then an extra box on the outside of the blown ion 125 to where you can add these gases. So there's a couple of changes that have to be made for both of those, but we can definitely do that.
And some would like to know what would be the advantages to using gases as opposed to just compressed air?
The only real advantage is if you're dealing with certain materials that don't treat well when you oxidize the surface, because what we're really doing is oxidizing the surface and putting polar groups on the surface with compressed air. Examples of that might be certain cases with rare metals like gold, or in copper applications for electroplating. They generally try to reduce the oxides on the surface instead of increase the oxides on the surface. I might argue that that's not correct in all cases, but that's a different discussion. But if for some reason, I've heard that argon works better on fluoropolymers. Oxidizing a fluoropolymer doesn't seem to work very well, but argon apparently does a little bit better job, but you're still going to have trouble treating fluoropolymers. It's just a difficult application. But that's usually why. If you don't want to oxidize the surface for whatever reason, you might try a different process gas, and that might be a forming gas, which is just a nitrogen-hydrogen mix. You could use just complete nitrogen, and that would do some cleaning of the surface, but it adds fewer polar groups to the surface.
Is treatment effective on nickel?
Yes.
Are you aware of any methods used to test the cleanliness or effectiveness of plasma cleaning on populated PCB boards?
I've got to think about that one a minute. The two methods that I have generally seen used to test cleanliness, one is a luminosity test. The other one is called an OSI test. And that is a photoelectric effect. So that one would probably not work on the entire circuit board, but it would work on anything that is conductive on the circuit board, because you have to have, for the photoelectric effect test to work, you have to have a conductive surface. So basically how that works is you shine a light onto the surface, and due to the photoelectric effect, electrons bounce off of that surface and go to a detector. And then that detector counts the number of electrons that comes back. So if you have a very dirty surface, you might get a number like 2,000. And once you clean that surface, it might go up to 10,000. So that you can get some relative numbers there. And the luminosity test is a visual test too, but it will work on any surface. So a PCB, you probably wouldn't try. I would look up luminosity testing for cleaning, and you should be able to find something there.
Concerning the new nozzles, the custom ones for the narrower application, what's the smallest nozzle that we've developed so far?
I'm sorry, I don't know the answer to that question. I can find out though. So we should have your information. Let me get with the product manager, and I will send you an email once we get off. And but I apologize, I do not know.
All right, we're going to take one more question here, and if we didn't get to your question, we will follow up with you after. You can also reach out directly to Wilson, either by email or phone. The last question here is, is there any residual coating with the flame system treatment comparison to the ion system treatment?
Any residual coating? No. Again, with all of our systems, we're just affecting a couple of layers, molecular layers on the surface to increase the polar groups there, and sometimes the disperse energies. But there's not a coating that we're putting on. There are coatings out there that can be applied with plasma. We do not do that. There's also coatings that can be applied with flame, but we don't do that as well. We're just usually cleaning and activating the surface and not putting any residual coating on the surface.
All right. Thanks, Wilson, and thanks to our audience. If you enjoyed today's webinar, if you learned something, let us know. Send Wilson or myself an email or give us a call. If there's topics in the future you'd like us to cover in this format, please let us know that as well. Hopefully we can help you out down the road. Everyone will receive access to the webinar as soon as it's processed and available online. You should get an email tomorrow. And with that, that'll conclude today's webinar, and hope everyone has a great day.